What specific problem with the CycleGAN framework does your proposed method address, particularly relating to cycle consistency loss?
The proposed method addresses the issue of cycle consistency loss in the CycleGAN framework, which is enforced at the pixel level and assumes a one-to-one mapping between image domains. This strong assumption can lead to unrealistic artifacts, as it does not account for potential information loss during translation. For instance, in zebra-to-horse translation, the generator struggles to remove zebra textures due to the rigid cycle consistency requirement. The modifications suggest a weaker notion of cycle consistency by incorporating CNN feature-level losses alongside pixel-level losses, allowing for more flexibility in the generated images while still maintaining structural integrity. Additionally, the method proposes to weight cycle consistency loss by the quality of generated images, which helps prevent the generators from getting stuck in local modes with unrealistic outputs.
How does the proposed method or algorithm work? Please illustrate the steps involved in your approach.
The proposed method modifies the CycleGAN framework to improve image-to-image translation by addressing issues with cycle consistency loss. First, it introduces a weaker notion of cycle consistency by incorporating a loss based on CNN features extracted from the discriminator, allowing for more flexibility in the generated images while still maintaining structural integrity. Second, it implements a decay mechanism for the cycle consistency loss over the training epochs, ensuring that early training stability does not hinder the realism of images generated in later stages. Third, the method weights the cycle consistency loss by the quality of the generated images, as assessed by the discriminator's output, which helps prioritize generating realistic images before enforcing strict cycle consistency. These modifications collectively aim to reduce artifacts and enhance the overall quality of the generated outputs while maintaining the core principles of the CycleGAN architecture.
Can you provide a specific example to demonstrate how your modified cycle consistency loss affects the output of the generators during training?
A specific example demonstrating the effect of the modified cycle consistency loss on the output of the generators can be seen in the zebra-to-horse translation. Initially, the generator learns a near-identity mapping, where it maps yellow grass in the zebra images to green grass in the horse images by training epoch 10. This behavior is influenced by the cycle consistency loss, which encourages the generator to produce outputs that share structural similarities with the input images. However, the modified cycle consistency loss, which incorporates CNN feature-level consistency, allows the generator to focus on maintaining realistic zebra stripes rather than strictly matching pixel values. This adjustment helps prevent the generator from being overly constrained, thus enabling it to produce more realistic outputs while still adhering to the essential structural features of the original images.
What theoretical or practical advantages does your proposed method offer over the original CycleGAN, particularly in terms of reducing artifacts and improving realism in generated images?
The proposed method offers several theoretical and practical advantages over the original CycleGAN, particularly in reducing artifacts and enhancing realism in generated images. Firstly, by introducing a modified cycle consistency loss that incorporates CNN feature-level consistency, the method allows for a more flexible interpretation of cycle consistency, focusing on preserving general structures rather than exact pixel values. This adjustment helps mitigate issues like the inability to remove zebra textures in horse translations, which was a limitation of the original framework. Secondly, the gradual decay of cycle consistency loss during training prevents it from becoming an obstacle in later stages, allowing generators to produce more realistic images as they progress. Additionally, weighting cycle consistency loss by the quality of generated images ensures that the focus remains on generating realistic outputs, especially in the early training phases, thus avoiding local minima where unrealistic mappings could occur. Overall, these modifications lead to outputs that, while not always pixel perfect, exhibit greater realism and fewer artifacts compared to the original CycleGAN.
In your experiments, how do you validate the effectiveness of your proposed modifications? What specific metrics and datasets do you use to compare the results with the original CycleGAN?
In our experiments, we validate the effectiveness of our proposed modifications to CycleGAN by comparing the results on the horse-to-zebra dataset. We utilize a constant learning rate followed by a linearly decaying learning rate for training, and we assess the quality of generated images by analyzing the presence of artifacts and overall realism. Specifically, we compare the outputs of the original CycleGAN with those of our modified version, noting that our changes yield better results with fewer artifacts, even though the reconstructed images may not be as close to the original inputs. We also observe that the weighting of cycle consistency by discriminator output does not significantly enhance result quality, likely due to the discriminators being jointly trained with the generators. Overall, our modifications lead to more realistic outputs, demonstrating their effectiveness in improving the CycleGAN framework.
What limitations have you identified in your proposed approach, especially concerning the balance between cycle consistency and preventing hallucinations in generated images?
In our proposed approach, we identified that while relaxing cycle consistency can lead to more realistic images, it may also allow generators to hallucinate unwanted artifacts, such as zebra textures appearing around horses. This indicates that the modifications to cycle consistency might be too lenient, resulting in a loss of control over the generated outputs. Additionally, we observed that the effectiveness of weighting cycle consistency by the quality of generated images did not significantly enhance result quality, likely due to the discriminators being trained alongside the generators, which limits their early-stage effectiveness. Furthermore, we noted that the overall result quality is highly sensitive to parameter tuning, suggesting that improper adjustments could exacerbate the issues of hallucination and artifact generation. Therefore, better parameter tuning is essential to strike a balance between maintaining cycle consistency and preventing excessive hallucinations in the generated images.